Well, in this second session dedicated to present the innovations of the project, we will tackle all those parts concerning to the performance of the battery. Okay. So what I presented at the beginning regarding the range anxiety or those drivers that move the end user to adopt the electric vehicle as their priority for mobility. No, that includes battery range, battery lifespan, the charging, the time needed to charge your battery, and all these parts refers to different technology domains, from the cooling system to keep the cells at the adequate temperature, the possibilities of applying ultra fast charging strategies to charge our batteries. Also, all the topic concerning the brain of the battery, how the battery is managed by the battery management system, the automatization system to control this thermal management system, the ultra fast charging, etc. And also other innovation related to this on wireless communications that we applied in MARBEL, and also the use of digital twin and AI for prediction of the status of the battery. Okay, so to start this session, we will start talking about the cooling system design in MARBEL battery. Okay, for this we have the opportunity to listen the presentation from a colleague from ABL Deutschland in Ingolstadt, Sandor Eschinger. Sandor have been leading the design of the thermal system. Okay, he's a technical lead in battery simulation in ABL Germany, have a PhD in engineering science, and well, he's been involved in different various customer projects in ABL and also in research projects. Okay, with expertise on cooling assessment, thermal and hazard behavior of the battery systems. So Sandor, if you want, the floor is yours.
Thank you, Eduard. Good morning, everyone. So today I'm going to talk about the cooling system and its functionalities, what we integrated in the MARBEL project. This is more or less the outline of my talk. So I'm going to introduce first the physical layout of the cooling system. And then I'm going to talk about the battery thermal management as a software, a control algorithm, how we developed it, and at the end, I will give a summary and outlook, what could be the next step and what we achieved during this project. So let's start with, let's say with the smallest increment of our cooling system. We have a cell which, let's say, is a given. In this case, we are not. For us, is a kind of black box, but for sure we want to ensure that the temperature conditions are sufficient for the requirements. So the U cell is also somehow defines our performance, our cooling performance. Because in this project, after changing of the cells, at the final stage, we have like a state-of-the-art cell, which with the current 2P or even 4P configuration does not really demanding from the cooling system. So that's why we have chosen a cooling layout, which is sufficient for this cell. So there are other techniques outside, more advanced, more sophisticated, but for the cell, that was sufficient. So let's say we have the cell, we want to, let's say, ensure the temperature homogeneity and the good thermal resistance. So we applied a thermal pad on the side of the cell, and then also the cooling fin, as you can see, is there. And the cooling fin should provide the thermal bridge between the cell and the bottom cooling plate in this case. We have the terminal, was in a previous presentation already mentioned. This is welded to the cell terminal, and yeah, it has bolted connection, which then allows us some advantages for the modularity, for the assembly process, and so on. And closing up the smallest increment, we introduce also a compression pad, which has more functions. First of all, it accounts for the swelling and breathing of the cells during operation, but also can slow down thermal propagation in case of thermal event. So this is more or less how the cell is then built up together, and then we can switch to the higher level of the battery. So we have the cell, and then we build up a module which consists of 12 cells with 2 P connections. And regarding the cooling system, we have, as I mentioned, the bottom profile, which is then flooded with the coolant. In order to provide a good thermal connection, we introduce a thermal pad in between the fins and the bottom profile. The same applies for the top cooling rail. The necessity of the top cooling rail was already also mentioned in the previous presentations. Because of the bolted connections of the bus bars, there is a risk of some local hotspots. And in order to eliminate those hotspots from the, let's say, we want to have a even temperature distribution in the cell. In order to eliminate this disturbance, we decided to have a top cooling rail, and it is also connected via thermal pad to ensure the good temperature connection. It's going to the next level of the battery. We have, like, I'm showing here the complete pack, which then consists of this is the bigger one with the 32 module, the bigger energy capacity. And in this case, we have 4 modules in a row, and we have like 8 rows from a cooling perspective. So we want to have a good temperature distribution between the cells. We made an estimation how many modules you can, let's say, place in series. With that, we will have a kind of temperature difference between the first module and the last module because of the coolant is heating up. The coolant is practically from the coolant distributor goes towards the end of the battery and then reverses. So that means we will have a temperature increase in the coolant. But as I said, with 4 modules, we are still satisfying the requirements. The temperature difference is not that high. I'm not going to show every details because of the time, but we checked it. And so what I also want to mention here is that the coolant distributor is very simple. It consists of the simple piping, and of course, in order to have the same temperature distribution in each parallel row, this has to be all of the parallel rows has to have the same flow condition, the same amount of flow. So this is done with throttles. I'm going to explain this in the next slide. And as you can see, the cooling system as well is modular because it's also already mentioned, we have 2 different sizes, and it's quite easy to adapt the system because it's just shorter profiles, or even in case you can remove the top cooling because it's quite easy. So it's a modular concept. So let's go to the one with the throttles. So as I mentioned, we have the two rails, the top and the bottom, and in ensure this homogeneity of the flow distribution, we introduced some throttles, so diameters in the inlet side of the coolant distributor. This was done with automatic optimization algorithm with simulation, and later on we checked it with testing as well. So the distribution is predefined, but it's also validated. So with this, we have a quite even distribution. So in theory and also in practice, we will have the same condition in each parallel law for the temperature distribution. Yeah, to provide a connection between the hardware architecture which I introduced, we need to, let's say, provide some sensors to the thermal management system, so the control algorithm, so the software side. So as you can see, we also based on simulations, we place the sensors in a position of the cell where we accept the highest temperature. With that positioning, so we can ensure that the battery is in a safe operation, or at least we have indication of temperature in the maximum position. So that helps me to go to the next slide, where I would like to explain the, let's say, the thermal management system a little bit. So on the left-hand side, you see the physical hardware of this. So we have the sensors implemented. So it's communicating with the modular BMS, which then provides us information like temperatures, voltages. So all this information is then channeled to our battery management system. So we have the current in this case, we have some temperature vector, time dependent, everything, and some other parameters, which I'm not listing here, but you can imagine it's like 16 parameter, which then defines our state, because our BTMS is a state-of-the-art state machine-based algorithm, but it has some special functionalities, which is quite new, and we developed during the MARBEL project as well. I call it as a digital twinning, but we can call it also as a virtual sensor, if you like, because our this model is a kind of physical-based, very simple model, which then allows us to, based on some sensor which are located in a, let's say, the predefined position, we can compute the local maximum minimum position in the battery on the fly. So this is a fast running model, which then help us to which allows us to have a precise thermal management in that sense, because for the aging and for the degradation, you want to avoid big temperature differences in the battery cell. And with that, you can ensure that degradation is more or less in the same speed in every part of in every cell. So this is needed because we have this very ambitious goal about the lifetime. So this is one feature what we implemented. It's also capable of preconditioning. It's one of our future steps that we are going. If we have a model that can. It's beyond MARBEL, because MARBEL is just focusing on a battery pack itself. But if you have a thermal management system of a vehicle, you have some strategies, and so you can develop a model which then gives you when the battery need for has a need for preconditioning or temporizing for, let's say, if you have a cold condition outside, you want to have a fast charge, you can maybe perform heat up from the grid, so you can save energy, you can save distance, and so on. So this is also an important feature. Now I would like to talk about one aspect of the development of this BTMS, because I talked about this fast running model. So in order to train our model, which is not an AI based one, we developed a high fidelity simulation, which a kind of co-simulation using P2D electrochemical model for the heat rejection, coupled with the FMU technology and the 3D simulation. We have a BTMS also coupled to this, and this simulation also considers the flow, as it's a conjugate heat transfer analysis, also accounts for the ohmic losses on the bus bars, the thermal contact resistances, the electrical contact resistances of the bus, the bolted connections. So all this together gives us a high fidelity 3D picture of the temperature field. This simulation, of course, has to be validated, which is also scope of the MARBEL project, but it relies on the measurement data, which is then going to be, let's say, it's ongoing at the moment, but the method is already there. So with this simulation, we can practically do some driving cycles. It's running actually quite fast, but on a supercomputer, you can perform the simulations actually in a short time. So then I'm going to explain now our fast running model. With this high fidelity simulation, for example, we can perform a series of 3D simulations, and using those signals, so we have now practically the temperature signal for every location of the battery. We can, let's say, in this case, in this slide, I'm showing the temperature, the driving cycle on the right-hand side. You can see it consists of an intensive driving and then charging, and again some driving. During this period, we can have, we can measure, we can log the temperature signals in different positions, and on the this one, so you can see that we have here curves with a straight line and dotted line, and the straight line is us from the simulation, and the dotted lines are from the model or fast running model, which captures the positions. Let's say this is the one which I took here. So BP cold is the black one, captures quite well the position of the minimum temperature, which is we expect to be here. So with this, practically, we could reduce the number of sensors. So this is also one possibility for the development of the MARBEL project, that we can get rid of the sensors if we are able to use this fast running model of the thermal management system. Another example where we need this is, as I said, the local maximum and a local minimum temperature can be also estimated with this model. So here in this picture, you can see the temperature difference, what we can sense based on our. Yep, I will. This is my last. So with the black one is the temperature difference what we can sense with the predefined sensors, and this is only indicating 2 Kelvin. But in reality, we have like almost 5 Kelvin difference in the battery. So actually, maybe we don't have the necessary information to condition our battery well. So our model is providing us a much better approximation of the temperature difference. So with this information, we can improve our thermal management. So this is my summary. So in point of view of cooling system, we let's say our cooling system fulfills the requirements, what we defined in the beginning of the project. It also considers this easy assembly, disassembly aspect, sustainability aspect as well. The system is scalable. We are introduced smart place sensors, and we have also a smart algorithm which is able of some advanced functionalities, which is quite interesting. And with that, I can, let's say, conclude my presentation and give place for the next one. Sorry for.
So thank you very much, Sandro, for the presentation. Well, and now as you see, we work deep on the thermal management because we were preparing it for the strategies for ultra-fast charging. And now it's my pleasure to present you one of another partner in MARBEL, Alberto Gomez, and he's e-mobility advanced engineer master in Ficosa Automotive. But a part of being a partner of MARBEL, Alberto was engaged on the preparation or the conceptualization of this project. He teamed up with me in the coordination as technical coordinator of MARBEL. And I think 2 years ago, he moved to lead this e-mobility engineering group in Ficosa Automotive. Alberto has graduated in physics for the University of Barcelona. He holds a master in energy engineering in the Polytechnic University of Catalonia, and also a PhD in nanoscience and nanotechnology in the University of Barcelona. He has experience in the automotive. He has been leading the mobility lab an energy storage lab in Eurecat. And now he's leading the mobility advanced engineering department at Ficosa. So he has a large experience in research in the sector and the batteries. So it's my pleasure. The floor is yours, Alberto.
Yes. Hello, everyone. Alberto Gomez, thank you for the introduction, Eduard. Now in Ficosa Automotive, leading the advanced engineering activities. What I'm going to present to you is what Ficosa was doing in this project, mainly the high voltage safety, and also the all the strategy on the architecture of this battery pack, the switchable that was mentioned before, just to be able to fast charge or ultra fast charge the battery, which was one of these objectives of the call in which we submitted the proposal. So first of all, a bit of Ficosa. Ficosa was established in 1949 in Barcelona, so 5 years ago, last year. Now we are global partners with Panasonic. More than 8% of sales are invested in R&D, present in 17 countries, more than 8,000 employees, 1.3 billion euros in sales. This is our global footprint. We have not only technical center in Barcelona, but also plant, commercial offices, and research centers around the world. Of course, for example, for the e-mobility business unit, we have also plant in China. Okay, so this is our customer diversification. Basically, Volkswagen is one of the main clients that Ficosa have. Also, Stellantis is the second one, Ford, and so on. Present in Europe, NAFTA, Asia, and South America. And we are divided in two vectors: mechatronics, which is e-mobility, and command and control for the gearboxes, and vision, which is another one of the historical parts of Ficosa. So the rear view systems, we are top 3 manufacturers in the world for mirrors. And the natural evolution of that is ADAS, with the surroundings and all the things needed for the autonomous driving. Okay. So this is e-mobility. We have 5 families of products: multi-sensing boxes, battery management systems, energy converters, communication boxes, and obviously the junction box that we developed for the project. We wanted to focus on the junction box because we had several things clear more than 5 years ago when we were involved in the proposal phase. So we had two things clear at that moment. In 2019. So one is one was that we had to avoid the use of copper as much as possible in the vehicle. That was clear. And the second one, that probably there will be a transition phase between 400 and 800 volt architectures in the automotive sector and the charging sector. So this is applying more than 5 years from that period. So it's same thoughts are applying today. So avoidance of copper, as mentioned before, it's not yet critical raw material, but it's going to be for sure. For the moment, it is strategic raw material. So to avoid as much as possible. And obviously, for the moment, we don't have a clear view on when 800 volts and beyond 800 volts architectures will come. So we wanted to focus on the one of the main objectives of the project, the decrease in charging time, so 25% in charging time. So what we bring to the table is the safety part of this. So how to ultra fast charge the battery without compromising the safety of the battery and the cells. And so that was one of the other one, the decrease of battery weight. So we are not only decreasing the weight by means of the replacement of aluminum copper busbars by aluminum, but also working on how to define an architecture, switchable architecture, but at the same time avoid too many contactors, no? So decrease the weight of the junction box. And obviously, since we can ultra fast charge more times in the lifetime of a vehicle, thus we are also increasing the lifespan of it. So we were, as I mentioned, we were thinking in two things. One of the copper that I will mention afterwards. The other one, what was the scenario in 2019 on the market share of 400 volt chargers, 800 volt chargers, and the situation is very close to what we are having 5 years from that. So today, so we still have 400 volt architectures in vehicle. We have still 400 volts architecture in chargers. Some vehicles have 800 volt architectures. Some chargers 800 volts, working on 800 volts. No, but the market share of them all are really different. And so we knew that we had to develop a product that could be versatile enough for the automakers to have a tool to be able for their cars to charge at 800 volts, although the architecture was 400 volts. No, you may think as well of another strategies, such as, for example, DC converters or DC boosters to be able to increase the voltage when charging. But we think on another one. We think on implementing a switchable architecture on the junction box. No, obviously 800 volts has a lot of benefits in terms of ultra fast charging and so on, but it has a lot of drawbacks as well. One of them is safety. No, so this is why we wanted to tackle safety with the junction box and not just include a DC converter to boost the voltage. So yeah, the idea of Ficosa for this project was to work on this switchable architecture to be able to charge, so vehicle working at 400 volts to charge them at 800 volts, and the other way around. So vehicles working at 800 volts to be able to be charged at 400 volts chargers. Okay, as a transition phase up until the moment that everything is working beyond 800 volts. So switchable architecture was one of the ideas we bring on the table, as you can see here. So we can have two halves of the battery working at 400 volts, but then that may be connected to either the charger or the inverter at either 400 volts or the other. So that was the versatility we were finding, we were searching for. Decreasing the cell stress when charging at more than 150 kilowatt, which was one of the key points of the project, increasing thus the battery lifetime and safety, and obviously only work on 400 volts when necessary for the safety reasons. As I mentioned on the copper, so we had clear that we had to remove the copper as much as possible in the vehicle, and to do so we were planning on going to aluminum busbars inside the junction box, and that will decrease environmental impact, cost, and weight. But as Agrati mentioned before, there are several challenges related to that. And there were several challenges in 2019 when we were thinking about going this step forward. And so obviously, sustainability is better going to aluminum versus copper, and the weight is decreased. So that's a good thing. That's a good thing, but there are several challenges. there are several challenges, no? So we can decrease the weight of the bus bars by 50%, going from copper to aluminum. Obviously, aluminum has a lower conductivity than copper, so obviously you have to increase the section for this conductivity to be the same. But comparing apples with apples, we can decrease the weight of the bus bars by 50%, going from copper to aluminum. But what's the drawback? Obviously, as Agrati mentioned, we need coating here. Why we need coating? Because when obviously our bus bars are made with aluminum, but they have to be connected to copper-based bus bars on the components that we have, so relays, contactors, and so on. So that's a problem, no? What to do with the alumina layer that instantly is created on the surface of the bus bars? That's the first one that Agrati also mentioned. But the other thing is that what to do with the galvanic corrosion that is generated, no, when electrically connected copper and aluminum, no? So obviously that was a thing that we solved in the project by means of implementing nickel coating in the bus bars. But obviously that's against sustainability. So I have to be honest, no? So we decrease weight, we decrease cost, we decrease environmental impact in the sense of going from copper to aluminum, but still there is some thin nickel layer there that when recycling, it's going to be very difficult to separate. But that was what we implemented in the project, no? But obviously in a beyond MARBEL project that can be obviously solved, and now we know why and how. So that's not a problem, but this is what we did in MARBEL. Obviously, we optimized the housing of the junction box to obviously decrease the environmental impact associated with the polymers that are polypropylene or polyamide that or carbon fiber or glass fiber that is that are the components of this housing. And so we decrease the weight, we decrease the volume of this housing to decrease weight and cost, but obviously plastic is not recycled. So that's another drawback. So we couldn't find a way to manufacture this housing with either polypropylene, polyamide, or glass fiber coming from a recycled way. That was in 2021, 2022. That is solved now. And so yeah, well, actually, that's the end of the presentation. But before that, I wanted to say that all the drawbacks can be solved and are solved, but the critical thing is when chargers and OEMs will, let's say, talk to each other to be able to solve these 400 volts, 800 volts, let's say, discussion and basically be able to move to a more weight reduction architecture, which is basically going to a stable voltage. No? The switching architecture obviously increase the weight in terms of adding some more contactors to derive the current, but yeah, that's it. So that was what we bring on the table tomorrow. Thank you very much.
Thank you very much, Alberto. Okay, thank you, Alberto. The presentation. Now we show how we manage the heat, how we manage the high voltage electricity. Now we are going into the electronics part and what concerns to the BMS, the brain of the battery management system. And the topic will be introduced by the leader of the work package that have been working on this, that is Lluís Trilla. He's industrial engineer from Polytechnical University of Catalonia and have a PhD in IREC, that is the Catalonia Institute for Energy Research. He's currently the head of the Power Systems Group, research group in IREC, where he works on different fields, such grid integration of renewable power, grid codes, and analysis and battery management systems for new battery types and electric vehicles. Well, welcome, Lluís. The floor is yours.
Thank you, Eduard, for the presentation. Let's take a look at the BMS that we have developed for the MARBEL project. Well, we wanted to work in 4 different pillars here. One is to provide a wireless solution, but also it has to be modular, flexible, and connected. By modular, we mean that it should be able to operate at different levels of voltages, power, and so on, and flexible for different types of applications. So this is the architecture that we developed for the wireless solution. We are transmitting the data from the cell directly to the module controller, and then from the module controller to the VCU, the battery control unit. As you can see here, we developed actually 2 solutions. One is the Bluetooth one, and the other one is LIN. In this case, we developed it as a backup solution. Okay, there were a lot of challenges operating only and risks operating only with a wireless solution. And since we wanted the project to be a success, we prepared this backup one. Actually, you will see here in the entrance some samples of the device that we have used. This one here is called the ISCM, stands for the Integrated Smart Cell Manager. You can see here in the picture where it's located in the modules. And you will see outside that there are some of the samples. There are actually 2 PCBs, one on top of the other. One of the PCBs is transmitting via LIN, and the other one is transmitting via the Bluetooth. So if some manufacturers prefer one solution or the other, or both, they can pick the solution that they want. And of course, I mentioned that we wanted to have a wireless solution, so to remove completely all the cables from the battery pack. And you can see here that there are quite a lot of cables, but this is for the LIN solution because there was, of course, this risk by the end of the project. And we will target it to have these characteristics. It has to be something very small and compact, has to be located on top of the cell, and there's not much space because you have this safety valve here, and then you have the bus bars and the terminals and so on. We need fast enough communication, but also to have a low power demand. We don't want to over discharge the modules and the battery, and of course, it has to be something cost effective and comply with all the EV standards. So on the modularity side, you can see, and as Alberto has explained, we have a solution that should be able to operate with 400 and 800 volts. So what we propose is to have 2 400 battery packs that are interconnected in them. So in this case, we can just have half of the system. As Tony was explaining, we have this modular design. So you can have one single battery pack, 400 volts with one VCU, or you can have both of them and have 800 volts. In our case, we limited the design to 1000 volts, but of course, this could be expandable and increase the battery voltage if necessary. If in the future it becomes a standard. And we can also use different stack configurations just by means of a software update. We can reconfigure the battery in different ways. And we wanted also just to make it even more difficult for us. We wanted to be able to operate down to a single module. So to operate from a 24-volt single module up to 800-volt battery pack. This was quite a challenge. What we did is to modify the module control unit. So by enabling by software, it can actually operate as a simple BMS. It can measure the current, it can operate and trigger a contactor, yes, safety, and it can provide a calculation of the state of charge. So this is something that we were developing also for secondary uses. This is also related to the flexibility that we want to provide. And we have also the connectivity. In this case, well, we wanted to send data to a cloud in order to provide some advanced features there, also to calculate some more specific indicators about what is the battery state. In order to do that, we had to provide some cybersecurity layer just to prevent some data tampering or unauthorized access to the BMS and so on. And by means of that, instead of only having what is running in the VCUs, the standard equivalent circuit model, this is due to the limited computational capacity in the cloud. We can have some advanced estimators like the state of health of the remaining useful life. Since we wanted also to have some feedback and to provide some data from the cloud back to the VCU, This enables some hybrid modeling combining ECM and a machine learning-based update of each parameters. So on this regard, we had this, for instance, we had these indicators, and these are calculated via mathematical or empirical models that we can develop in a laboratory or black box approach using data-driven, but we can have this gray box modeling, so we can update the equivalent circuit model or any other models that are running in the VCU, in the BMS, according to the aging and the evolution of the battery system. So depending on the type of driving profile that we have, all the environmental conditions that the battery is under use, it will degrade in different ways. So we can update all these parameters in the BMS so it can track more correctly, and it allows us to better handle what is the battery evolution. And here is some example of the data visualization that was developed for the project. All these details about what is running in the cloud will be provided in the next presentation by CCS, who are the ones behind these developments. And this is just for any user to be able to interact with all the data that has been uploaded and stored in the cloud. And you can have some feedback. For instance, you can explore different applications, or just to decide when is the moment to replace a battery or to fix anything that is maybe not working properly in the battery system. Then for this connectivity, of course, if you have all this information, there are some end-of-life management that we can use here. On the one side, we wanted to provide some second life applications. This is something that, in this case, you can be doing without any testing on the battery, because you have all the information up in the cloud. You know when the first life is over, and there's some remaining use for that battery, and actually you can interact with the model, the data-driven model in the cloud, to experiment on different second life applications. So you can decide which is the best way to go. And if you, with these advanced models, you can decide that there are no further use for this battery, so it can go directly to recycling. And this is something maybe Farouk later from TEFREC talking about the recyclability of batteries. Will appreciate, because sometimes they don't know, they have no information what is the state of a battery when it's coming to the recycling plant. And in this case, if it's something that we can link, for instance, with the battery passport, it's an information that any company interested in that information can have on all the historic life and the safety or the condition of the battery when it's being received at the facilities. In our case, we wanted to, well, in this circular approach, wanted to study one particular second life application, which is the reusability for urban light electromobility. As you have seen, these modules have the shape and also the voltage levels and power levels very similar to the batteries used in these kind of applications. And since the module control unit can act as a BMS, it's a direct second life. There's no need for refurbishment. Just a simple modification of the software that you can calibrate to activate this, enable this second life use. And it's a direct reuse of the battery, which can provide an extension of quite 5 to 8 years of the use of the battery. And this is having an impact also on the cost, economic cost and environmental cost of the battery, reducing the cost per kilowatt hour delivered over its lifetime. And well, finally, this is, let's say, next steps. We have seen that we have this wireless communication, and as I explained, it's going from the cell to the module controller and to the BMS, because we wanted to have this modular configuration, but it should open also the door to have some cell pack configuration, so transmitting the data directly from the cell to the VCU, so you can remove quite a lot of dead weight, in this case, not only connectors, cables, but also the module housing. So it's something to further explore. And well, this is the list of all the features that I have been explaining. As you can imagine, it's been quite a challenge to develop a BMS that is able to operate from single module, to 800 volts, different applications, wireless and wired solution with communications, also the connectivity, and well, to develop all these features all at once, make it work. We had the help, of course, of a lot of colleagues from MARBEL. Fortunately, that's not the company behind the BMS working with us is PowerTech Systems. They cannot join us today. But we have here the colleagues from OTC Engineering. They were the people behind the ISCM. And of course, if you want to interact with them, they have a lot of very interesting solutions for the automotive sector. And that's all from my side. I'm on time. Thank you very much.
Great. Thank you, Luis. We are on time. Okay. We see an overview of this battery management system. Now we will see what can be done with this data that the battery management system is collecting and managing. Okay, because one of our partners worked in the development of a digital twin and the application of machine learning and AI algorithms to make prognostics on this cell. And for this, we have the pleasure to count with Alexandros Bousdekis. He is a senior research scientist at the Information Management Unit on ICCS in Athens, Greece. He holds a PhD in proactive computing and event-driven decision-making with a focus on Industry 4.0. So he has been working on the application of this machine learning AI in various applications, industrial applications. So the floor is yours, Alexandros. You will explain us this part.
Okay, hello. I have a loud voice, so I will stand a bit ahead. So I'm going to present the battery digital twin that we developed in the context of the MARBEL project in order to support prognostics, battery prognostics with the use of machine learning and AI. So we, as ICCS, we are a research institute in Greece, in Athens, associated to the National Technical University of Athens, and ICCS ranks according to the EU official rankings among the top 3 institutions in Greece and among the top 20 to 30 in European Union, and it consists of several laboratories, among others, for software engineering, for robotics, for photonics, etc. And among them, this is our research team, which is the Information Management Unit, and we have been actively participated in 62 research and innovation projects, mainly funded by the European Union, by the European Commission Research Framework Program, Horizon Europe, and previously the previous framework programs. So our research lays on 2 research directions. I mean, as a lab, as a team. On the one hand, the one direction is about artificial intelligence and human AI collaboration in various application domains. One of these is the battery domain, the electric vehicles, etc. And the second direction has to do with cognitive computing continuum, again with several applications and several aspects related to this. So why do we need a digital twin for machine learning based prognostics? First of all, as also Luis presented, there are several data-driven approaches for battery prognostics, and especially during the last years, these approaches have been driven by the development of AI and machine learning algorithms. So this direction dictates the need for efficiently embedding various algorithms in one unified software framework in order to support various objectives, such as state of charge estimation, remaining useful life prediction, etc. So the experience and the results up to now show that machine learning and AI methods in this domain show a great potential, I mean, on battery prognostics. However, at the same time, there are several challenges that need to be addressed. First, they cannot be implemented by non-machine learning experts. so they put a barrier on wider accessibility from the domain experts, for example, etc. Second, the reconfiguration for new problems is laborious and time-consuming. The fact that an algorithm or a method or a system works fine for one use case, this does not mean that we can just put it to another use case and works equally fine. And third, up to now, there are mainly ad hoc, we could say, approaches without unifying the diverse data sources. For example, we can have either a case from cyclers data or from the battery management system, and they do not put all this together in order to have a single solution to handle this data. So the data-driven digital twin for electric vehicles batteries that we have developed embeds AI and machine learning algorithms in order to estimate state of charge or other objectives, state of health, remaining useful life, etc. It has been designed and developed based on Industry 4.0 principles and standards, because I know very well that standards are, especially in some application domains, like in the automotive domain, are very crucial in order to develop a software application that can be adopted by the industry. The architecture of the digital twin supports several dynamic predictive analytics processes, and it is capable of employing data from the heterogeneous data sources. And as I said, it is able to process both data derived from the cycling tests and data derived from the battery management system. So the digital twin, according to the platform Industry 4.0, is implemented by the asset administration cell. There are specific, there are very concrete specifications that have been published by the platform Industry 4.0. So we followed these specifications. And on the other hand, we follow the reference architecture of platform Industry 4.0, the so-called RAMI 4.0, because on the one hand, it ensures the interoperability among the various components, algorithms, and technologies, and on the other hand, it ensures that all participants involved share a common perspective and develop a common understanding about the application to be developed. So based on this, mainly based on the asset administration cell specifications and the RAMI 4.0 reference architecture, we designed the architecture of the digital twin, or in other words, we instantiated these standards, let's say, de facto standards, we instantiated in the battery domain for electric vehicles, taking into account all the specificities and the distinct challenges that the application domain has, and we need to address. Another thing that we realized during the MARBEL project was that due to the fact that, as I said, all these developments, these data-driven approaches for batteries of electric vehicles have been developing in an ad hoc manner, there was not a commonly acceptable data model which will manage and handle all this data that need to be retrieved, to be stored, to be processed by AI algorithms. So after having identified the two, let's say, main data sources, as I said, the cyclers and the battery management system, then together with the colleagues and the partners in the MARBEL consortium, we specified, let's say, the physical architecture of the battery and how this physical architecture is transferred somehow to the digital world, so how it is represented in terms of data in the digital world in order to support all the data processing pipelines and the machine learning pipelines that the digital twin implements. Of course, this is a high-level view, which is public already. We have also a more detailed view, which will be published, within the next weeks or months, with all the details as a conceptual data model in order to facilitate replicability in the interested users. So we also designed the conceptual architecture in order to support all these objectives, like the state of charge estimation, remaining useful life, prediction, etc. And we developed the solution as an analytics as a service platform in order to enable the development of several independent analytics processes with different scope. For example, for providing descriptive, predictive, and prescriptive analytics while having data from multiple data sources. So we integrated state-of-the-art technologies for software development, for interoperability, and for machine learning pipelines and AI in order to support this approach. As also it was mentioned in the previous presentations, all this digital twin runs on the cloud, and the data are transmitted in the case of the battery management system through an MQTT broker, but the digital twin is capable of also supporting other brokers and other message protocols. And in the case of cyclers, again, there is a flexibility there, either with a simple, let's say, data uplifting or other interfaces that have been developed in order to facilitate this interoperability and this transmission to the cloud so that the data can be processed by the digital twin. We also developed a graphical user interface. So the software has been paired with a web-based dashboard in order to enable users to interact and have access to all the general insights. So there is also an advanced filtering mechanism in order to provide insights based on the filtered dataset that the user provides, and see either during, for example, during the testing procedures and the experiments to see the performance of the cells and their evolution. And in terms of results, because this is probably the most important and convincing part, as I said, we embedded various machine learning and AI algorithms in order to calculate the state of charge, to perform early failure detection, to predict upcoming battery failures, to estimate the remaining useful life, etc. So on the one hand, we have data pre-processing mechanisms in order to obtain the data in the format required and to ensure their quality. And on the other hand, we implemented several algorithms, AI algorithms, ranging from, let's say, traditional machine learning to deep learning, automated machine learning, and transfer learning. And we applied the digital twin, all this solution, in two use cases. The one had 10 different drive cycles in 3 different temperatures, and there we achieved an accuracy for state of charge estimation ranging from 87% to 97.5%, and in a more extensive, let's say, use case with 124 datasets describing the whole lifetime of each cell, and they were created from different charging profiles. And there, since we had much more data, we achieved an accuracy for state of charge estimation ranging from 94 to 99%. And regarding the remaining useful life prediction, we achieved an accuracy of mainly between 85 and 90%, apart from one approach combining deep learning and transfer learning, which achieved 95%. So this we already extend this work, I mean, in order to validate it in several data sets, either from cycling tests or from battery management system data, while we also combined this approach to an ECM in order to provide a hybrid, let's say, solution together with other colleagues from the consortium, and to provide the state of charge estimation with this hybrid approach. You can also check our poster outside on the lobby, and afterwards in the Q&A session, but also in the break, I would be more than happy to answer any questions.
Great. Thank you very much, Alexandro. Thank you. Okay. Our last presentation in this session, last but not least, is related to the secure wireless communication system. And previously that you have seen in the thermal, well, in the different presentations, the ISCM. Smart Cell Manager. Okay, this presentation, this wireless, secure wireless communication and this electronic have been developed by an engineering company, OTC. And today we have with us David Gutierrez, that is industrial engineer and project manager in this SME in the region of Catalonia in northeast Spain. OTC has been working in innovation and R&D projects for more than 20 years, and he's involved in different areas and sectors. So he has an experience in projects related, linked to the connectivity and 4.0 solutions. Okay, so David, the floor is yours.
Thank you, Eduard. Okay, as he said, I'm David Gutierrez, and I will introduce you what is the ISCM. It was introduced before by Luis. I will a few deep insight of it. Okay, first of all, I will make a few review of what is our company, OTC, and then I will explain what is the Smart Cell Manager, its features, functionalities. We will see a plot diagram of what is inside, the results of the test that we've done, and the mechanical integration into the cells and the module. So, okay, OTC Engineering is an engineering firm that we're focused on delivering cutting-edge solutions to our customers. These solutions can be classified in three main topics: mobility, cybersecurity, and connectivity. We have the main headquarters at Olot in Catalonia, but we have also an office in Barcelona and in Delhi with software and hardware developers, each of them. So then our services for mobility can be divided in three main pillars: engineering, advanced product development, and software-defined solution. In each one of them, we can find consultancy for functional safety, cybersecurity, software development following a SPICE and B model, product digitalization, and then telematic units, motion control, wireless power transfer, digital key, and then software-defined solutions like secure photo, intrusion detection, prognostics, digital key, and also solutions linked to the cloud and user interfaces. So then, more specifically, what we can offer to our customers, it's a quick proof of concepts because we are very flexible and fast in engineering. Then rapid prototyping in electronics and software embedded and software intelligence, and also electronic and mechatronic products and smart electronics connectivity innovation and connected motorbike and smart connectivity solutions. So we have a deep experience in software development for the automotive industry. Then here we can see a schema of what we can, of where we can place all these things. And okay, then going from small services to connection to external systems, clouds, and user interfaces. Okay, so this is small words, what is OTC? Then I will go with the Smart Cell Manager. What is the Smart Cell Manager? The Smart Cell Manager is an integrated intelligent control module embedded in each battery cell. This module, it monitors the health and the performance of each individual cell, reading the temperature and the voltage from inside, and having the orders from the battery management system. And all this communication is done by a wireless system. In this case, it's radio frequency technology, Bluetooth. So this innovative solution eliminates the complex wiring inside the cell and enable local balancing of each cell and improving this functionality. So the key benefits of the integrated Smart Cell Manager are a simplified wiring. It reduces the wire inside the cell from approximately 20 meters to just 80 centimeters. Then it also lowers the material cost and weight because of this less copper and plastic needed inside. And also it's easy to assembly because it's less parts, less cables to wire inside to connect. And then it enhances the battery performance because it gives the measure exactly at the point without any losing of definition of the readings that is doing because of the connections. Then the key features that has the integrated smart cell manager, it's small and compact. It's embedded in the battery cell. It can go inside the casing or outside the casing. Yeah, and it integrates all the functionalities that needs to be done for manage the cell in a minimal footprint. You can see we have samples there outside. You will see it's very small. So then a low power consumption. It is powered directly by the cell. This ensures a continuous operation of it, but with a very, very few, we will see later, power consumption. Then also it's a cost efficiency, of course, because it's easy to assemble, less time to assemble it. And it can be produced in mass because it's for high volume production, because it will not, it's independent of the position in which it needs to be placed on the battery. And it's adaptable for different type of electrical vehicles batteries. Then the functionalities that has the smart cell manager are mainly the most important. I think it's the power management, because if not, it will drain the battery voltage. So then it has several operation modes depending on what is needed from it at each moment. It has the deep sleep, standby operation, communication, and balancing. This ensures that the consumption of the energy is optimized at maximum. Then it has the cell voltage sensing, and it does the cell passive balancing using an embedded MOSFET, and it reads the cell temperature. All these three values are communicated with the BMS by wireless communication, the Bluetooth low energy. And then when it's not working, it goes to a low power mode, as I said before, deep sleep, that it ensures that it will not drain the battery. Then at last we added a wired communication system for backup, just to be sure that that we can do the tests on the battery without having problems. But just for backup, it's just to double check that everything is working. Okay, then we can see here the block diagram of the functionalities that are inside. It's more or less a schema of what I explained before: the power management, the passive balancing functions, the cell and voltage sensing, the MCU function for control operations and processing data, and the communication blocks for Bluetooth and link communication. Then the result is this. So we can see the two PCBs that we told before. One PCB for BLE, one PCB for LIN. This is the temperature sensor and the power supply cables, and the LIN communication backup line for transfer the data from one CM to the other. Then for a final solution without this LIN backup option, we will have the PCB, the BLE PCB, with only the external NTC sensor and the power supply cables. So it avoids this, and this is why we reduce the connections inside the module. Okay, we have made some tests on this solution to check that it works. Then in the two main topics, it's the connection status and the power consumption. And the connection, this is only the test for BLE, because it's the goal of this project. It's to run with a wireless system. The communication is fast, it's less than 50 milliseconds, the process of connecting, data transfer and disconnection. We've made several tests that we reach up to 92% of successful connection tests In some of them is less. So it means that we need to do an optimization of this process that is in progress that in order to achieve a full connection. This was being tested while the battery pack is assembled, and it works properly with this BLE communication, and it could run good. Then also related to the power consumption, when the ISCM is working in balancing mode, the consumption is 3.7 milliamps. But when it's in a sleep mode, it is 3.2 microamps. So it's nothing for the battery list. Then the conclusion is that the ISCM operates efficiently with a minimal power impact. That is, as I said, is very important. This, and if lean needs to be used, just if it's chosen to do with lean, it's aligned with the automotive systems of 12 and 24 volts. So then, last, the mechanical integration. We can see here the cell and the ISCM here on the top. Then this is the cable for lean from one module to the other. This is the temperature sensor and the power supply cables. Then of this we have a new version of these cables that are shorter from this. Okay, well, I think that's all. So thank you.
Okay, great, thank you. Well, and thank you very much. Now it's time for getting questions from the audience, the in-person audience here in the auditorium and also online. So please, I would like to kindly ask the speakers that were involved in the sessions to sit here. I will share with you this microphone here. Right, thank you, Christian. Okay. Well, maybe we could start from people in the auditorium. Is there someone willing to pose any question about the different topics presented? Magnus from Sintef, please.
Hello. Yeah. Well, just a short question to David. Very impressive about the work with the ICSM. Two short questions. Why you have an additional electric cable as an additional? Would it be possible to use the already connected bus bars as communication to the junction box and the BMS? Would it be possible to use the bus bars and the high power cables to communicate?
Yes, Abby. Yeah, I suppose, but the idea is do it wireless, and then this lean backup solution was added later. So with the reason we did this with two PCBs.
Yeah, I understand.
And then we can remove the lean and keep the wireless communication.
I understand, but my question was, would it be possible to also use or in addition, or instead of the lean, use the bus bars?
I don't know. We need to check.
That could be.
It will be possible, I suppose.
Yeah, and the next short question: why isn't this technology already implemented in the batteries by the manufacturers of batteries? Because it seems to be very important and necessary. Why is it not already integrated into the batteries by the manufacturers like Cattle or Caterpillar?
I suppose that the wireless communication is a challenge, and now it's people want to be sure that if you put a cable, it runs. But maybe I think that there is a advanced on this on the BMS wireless solutions, but maybe they are still on a project.
Thank you.
Thanks.
Okay, thank you, David, for answering. I see another question or another.
Hello. Okay, I'm usually Vet, and I have two questions. One is regarding to the machine learning. With the algorithms that you have been provided, are you able to detect at the cell level what is the status of the health at the cell level?
It depends on the sensor placement. So in the case of the tests, where the tests are performed on the cell level, the outputs have to deal with the cell level. But of course, because I understand that you probably mean, for example, in the BMS, when you have on an upper level the sensors, how to see what happens in the cell level. So this has not been done. It was really challenging when you have parts, let's say, or a level where you do not have sensors because the behavior is not the same. So you need sensors on what you want to measure.
But in this case, that you have an individual sensor for each cell, should be possible?
Yeah. In the case of the cycling tests, the sensors are per cell and the outcomes are on the cell level.
Then you can decide it. For example, after the car has 100,000 kilometers, that some cells, their state of health is not good, and you can replace it.
Yes,
This is achievable. This is achievable.
Yeah. As soon as the sensors are placed on this level, yes, this is feasible. I mean, this is what we have done. Yeah.
Okay, good. And the second question is regarding to the thermal management. I'm sorry because I'm not expert on this, but I'm curious because you said that in this case of the type of cell used in MARBEL, the thermal management is easier. Then there are another type of cells which become more difficult, the thermal management part.
What I was meaning with this, that the cooling requirement depends on the fast charging strategy and the current in which is acting on the cell. And because of our architecture with the 800 volt, practically we don't have a very high current on the cell, even if we have a relative rapid charging. And also when it's because there are some limitations from the cell. The cell provider usually gives you the maximum available C rate for the cell, and all these things together defines you the requirements for your cooling system. So in this case, with MARBEL, with this architecture, with what we presented, there was no need. We did at the beginning so kind of feasibility study or concept study of different cooling systems like immersion cooling in a simplified manner, and it came out that for this spec is sufficient to have this kind of cooling system. So we don't need to use immersion cooling when it's not the application does not require that. So that's what I meant with that it's also based on the cell, it's based on the application. So, and for the MARBEL was this kind of cooling system sufficient. I hope I understand the question.
Got it. Thank you.
Great. Thank you.
I just add the best cooling system is the one you don't know, you don't need. Basically, is what no. If you don't need to do immersion cooling, then what's the point?
Yeah. So we also wanted to save space, everything. So it would be the best if you don't need any cooling. But okay.
Okay, thank you. There were a question there, or yes? Can you raise a hand so they can see you? Thank you.
Hi. With all these PCB and ICM connection, backup connection, does it make a big weight contribution on the battery pack?
No, that you mean that the PCB from wired communication? It works more or less the same with or without this. So we did the test with BLE and with Lean, and they work good with both cases. Thank you.
Great. And then there have been some questions also here online. For instance, concerning the junction box, there were someone asking about thermal. So if there is any thermal inconsistency in the junction box due to the fact that it's switchable, there is any oversizing needed there or any cooling needed for this?
So the best cooling is the one that you don't need. And so we didn't need any cooling to cool down the bus bars. So it was all by design. Normally, what we can do as well is take advantage of any cooling plate that it's on the battery to cool down as well the bus bars of the junction box. In this case, maybe put some of the bus bars, big bus bars, just in the bottom part of this. But no active cooling is needed.
Okay, thank you. Well, there is one for Luis that includes a question that I can answer while I read the whole one. But it's do you use one monitoring chip per serial node or cell in the BMS? Is the wireless communication Bluetooth? Yeah, I think this one.
Yes,
is the
and
one
yes.
that I know. Yes. Yes, it is. And is every chip communicating with the main by itself, or do you have a separate communication chip which combines several monitoring chips? I guess maybe they are.
Yeah, as I explained in the current architecture, we combine from all the module data is gathered on the module controller and then is sent to the VCU. But that step might not be necessary. So we can even further optimize more the battery design and go to a cell to pack.
Okay, great. Thank you. And well, maybe we have some more time for some more questions. Regarding the cooling, for instance, there were, I don't know if we remember sorry, about the what are the ranges of temperature we get it, no, for the when fast charging and when slow charging. The gradient, yes, that's.
Yeah, it's of course it depends on the environmental conditions as well, because the cell heat release is also depending on different parameters. But let's say if we have room temperature, like 25 degrees, and you apply our fast charging, then I think I'm not so sure about the values, but we are just below 40 degrees maximum in the battery. Mm-hmm. And the temperature spread during this period, of course, I'm repeating, if we have moderate conditions, then we are below our target, which is 10 degrees. But if you start from the very cold conditions, it might look different. Then we have probably a higher temperature spread at the beginning, which can be up to, let's say, almost 30 Kelvin, but that's decreasing because our control system tries to cool in a manner that, in the case, heat up in a manner that these temperature differences are reducing. And yeah, maybe that's answers the question.
Okay, great, thank you. Sandor, someone else was asking also about the cooling plate, if it's integrated in the box or not, or it could be.
It is integrated in the housing.
Yeah, it is.
Yeah. So it is below the. It's an integral part.
Makes part of the housing, the cooling plate. That was another question, and related to the last questions that there are here related to the machine learning algorithms, etc. And there were someone that was asking which kind of data are you using to train these algorithms.
Yes, we have taken advantage of all the data related to this measurement. For example, voltage, current, temperature, impedance, etc. I think these are we have identified that these are the most important parameters. Of course, the more the parameters are measured, I mean, the better the machine learning and AI algorithms can be trained. So yes, I would say that these are the main parameters. But of course, this is also the reason why we designed and developed the data model that I presented, because several parameters can be measured, and up to now, from a data-driven perspective, there are mainly ad hoc approaches to handle and to manage all this data.
Okay, great. Just the last question that is short, that I show here in the list, and also would like to comment that once we ended this last question, we are going to the lunch, and you will see the battery. It came while we were here listening all this. The battery came to us. So you will find it when in front of the building. No, last question. Someone was interested in the part of communications and how many, and it's about how many nodes of well, it's like nodes, but you know how many nodes. It's a limit of communication, I guess that would be, but there is a limit of the number of points of communicating information to the BMS.
Yeah, but it will not be achieved in a battery. So we have one node for each cell, but they are communicating with BMS, so it's only 6 for each one.
Okay, so they were asking like if there's how many, but it's
Yes,
like the limit is out of what
Yes.
would be
Yes,
in a battery.
and now we are 192 in the battery pack of 800 volts.
Okay, great. And apart from this, there are some congratulations about the innovations brought here today. So that I bring from the online audience to you. And
can say
I
thank
think
you.
I think it's well, it has been a very nice discussion. Thank you very much for providing these insights on the innovations and the work you are doing and the work you did in MARBEL. Well, a special thanks from my side as coordinator for the good job done. And well, now time to say hello to our battery outside and to make a break for lunch. Okay.